All right, I think I'll get started with today's session. Since no one has joined, I'll just go ahead and start teaching and probably you'll be seeing this video later on. So welcome to this week 6 TS session on optimization methods for civil engineering NPTEL course. So as we were discussing in the previous session, we solved some problems related to constraint optimization with equality constraint. So the content of this week's session will also be on constraint optimization, but it will be with mostly inequality constraints, and it can be with equality constraints as well. And there are two methods for which are using which you can solve such problems. So that will be the content of this session. Probably we'll take some examples and solve some problems related to those two methods. So let me write down the outline of today's discussion. And the two methods are, one is the Lagrangian multiplier method, which is also known as Kuhn-Tucker's method. And then using the second method, which is called the penalty function method. So this week's content are a bit easier than the previous, I think, week's sessions because it's only, I think, consisted of two lectures and very short videos. So problems will also be similar, I think, easy problems. And I think you have seen the assignment as well. The assignment problems are also probably not that difficult. I think you can solve it in within a half an hour or something. So let's take similar examples and solve such problems. So first I'll be discussing this Lagrangian multiplier method or the Kuhn-Tucker's method. So for that, what we have, okay, so first I'll write down, this is the Lagrangian multiplier method. So let's look at inequality constraints only. So for now, so constraint optimization with inequality constraints. Now, what you have right now is suppose you have given a function minimize fx, which is subjected to some function gx less than equals to 0. So this is kind of your standard form of such problems, and you can have in addition to this as equality constraints. But let's discuss about this kind of problem setup first. So if you have a problem like this, then in the Lagrangian multiplier method, first you have to write down the Lagrangian, the expression for Lagrangian. And as sir discussed in the class, if you know which ones are the active constraints out of this G constraints that I have written down here, so it might happen that it's not just one constraint that's present here, it can be multiple constraints. And out of those multiple constraints, only few of them are active constraints. Active constraints means the function gx, it's not less than equals to 0, it kind of becomes equal to 0, it's on the curve itself. And if the constraint is not active, then you have kind of a separate condition for that. And I think sir derived it and had some restrictions on the values of lambda. So let's look at that only. So you can write the Lagrangian function, which is a function of x and lambda, and you can write it as fx plus lambda times gx. Now, what you have here is this expression, and in the equality constraint setup, we took the partial derivative of this Lagrangian with respect to x and and also with respect to lambda and equated to 0. But if you see here is that, so this is your Lagrangian expression, So this is Lagrangian function. And let me take the partial derivative of it with respect to x. So it might be del x plus lambda del gx of del x. Yeah, so I hope this expression is clear to you. So this is just a partial derivative. Lambda is a constant here. And if you notice here, if you take the partial derivative with respect to lambda, oh, sorry, I have written it as y, it should be lambda. Then what you are left with is only gx. But now you cannot set it to 0 because you know that gx is less than equals to 0. So this is less than equals to 0 here. So this is kind of becomes irrelevant for now. So the conditions that you have, the optimality conditions, if you don't know which ones are the active constraints and so on, as mentioned in the class, here you have just one constraint. So first, what you can do, you have restrictions on this lambda values. So that sir, I think showed in the class by showing that if you take a direction, say grad of fx and multiply it with a vector, say s, then if this lambda values are positive or zero, then you have reached optimality. So you will only increase your function from that point onwards. You cannot decrease it further. So for the minimization problem, you have already solved that. So the restrictions for this lambda is that it has to be greater than or equals to zero. But before that, we have another constraint that has to be satisfied. So there are four conditions actually. So those which you have to satisfy. Once the primal feasibility. So you can think this as a primal problem and you can write it as its dual as well. So I'm not going into the details of it. So those are mostly for convex optimization problem. And here, if you assume these functions that we are dealing with are convex, fx and gx, so you are essentially dealing with a convex optimization problem, and you are guaranteed to have a global minima for this kind of problem setup. And then if you have some different kind of functions, then you are not guaranteed to have a global minima. So you might reach a local minima, and it may or may not be a global one as well. So let's not get into all that. So let's just look at the optimality conditions. So my primal feasibility tells you that this gx function, so if x is a feasible point, this has to satisfy. Then I have another condition called the dual feasibility, which is the same as the one I have mentioned before. So this lambda values has to be greater than or equals to 0. So this lambda values actually becomes the dual variables in the dual problem. So not going into that details of that. Third is the complementary slackness condition. So this is the complementary slackness. So this also, sir, proved it by converting this gx less than equals to 0 functions by adding some yj square or something and made it as an equality, and then had the condition of this uh, lambdas multiplied with the primal functions. So what you can have is that, so this lambda times g of that x, that feasible point, so that will be your equals to 0 in that setup. So it's either the constraint is active, so either it's gx equals to 0, or you have lambda equals to 0 in case the constraint is not active. So that's the condition here. And the fourth condition is that gradient of the Lagrangian has to vanish with respect to x. Of the Lagrangian function with respect to x has to vanish. So let's see. So that means I have already written this del L del X kind of expression. So this has to be equals to 0. So these four conditions, if you satisfy, then you have reached the optimal point. So let's try and solve an example problem using that. So yeah, anyone hasn't joined yet, so I'll just go ahead and start solving problems anyway. So let's take this example, example one. So I'll probably go a bit slow in this class because I don't know whether you're able to understand it in real time or not, since there is no one to respond. So anyway, I'll solve this few problems. So suppose I'm given max of xy. So this function I have to maximize, subjected to constraints say x plus y square less than equals to 4 and x and y is greater than equals to 0. So this is a simple problem. I think you'll find a similar problem in your assignment question as well. I've just modified some of the values here and there. So let's see how you can solve this problem. So whenever you have a maximization problem, the first goal of you is to convert it into the standard form, and you have to convert it into a minimization problem. So you can write it as min of minus xy, and you have the constraint as it is. Your next job is to write the Lagrangian function and just satisfy the four conditions. So what you can do is that your L is nothing but x. It is a function of now x, y, and lambda. So this first function, so this will be minus of xy, and then what you have is this first constraint corresponding to that. You can assume this Lagrangian multiplier as lambda 1, and for this two constraints, you can assume them to be lambda 2 and lambda 3. And you also need to convert this constraints into less than or equals to type. So what you have to do, you write x plus y square minus 4 less than or equals to 0. Then you have minus x less than or equals to 0. And then you have minus y less than or equals to 0. So these are your gx less than or equals to 0 type constraints. So you have g1, g2, g3 here. So that's why you have lambda 1, lambda 2, and lambda 3. So let's do that. So this is lambda 1 times x plus y square minus 4. Then you have lambda 2 times of minus x. Then you have lambda 3 times of minus y. Now you have to satisfy all these constraints, the x plus y square less than equals to 4, xy greater than equals to 0. So those are your primal feasibility. Lambda 1, lambda 2, lambda 3 has to be greater than equals to 0. So those are your dual feasibility. I'm not writing those two down. So those are kind of trivial. So the next two conditions, which is what we are interested in mostly. So first let's take the fourth condition, which is the gradient of the Lagrangian with respect to this x and y should vanish. So let me do that exactly. So what I can write is del L of del x. So this will become minus of y plus, so this will be lambda 1, then you have minus of lambda 2, and that is all. So that's the terms containing x. And okay, okay. Hi Jayasuriya. So I was solving one optimization problem, constraint optimization with inequality constraints. So this is the problem setup that I have, max of xy subjected to x plus y square less than equals to 4 and xy greater than equals to 0. So I was solving it using Lagrangian multiplier method. So whenever you have such problems, this max problem needs to be converted into the standard form of minimization problem. So that's what exactly I've done. I've made it min of minus xy. Then I have written the Lagrangian function. So it will be a function of x, y, and lambdas. And there will be three lambdas here because there are three inequality type constraints. And you have to convert it into this g x less than equals to 0 type constraints. So that is exactly what I have done. So I have taken this function fx and then plus lambda 1 times g1 of say x and y, and then lambda 2 times g2 of x and y, and so on. And the conditions that I have to satisfy is that one of them is gradient of this Lagrangian with respect to x and y should vanish. So I'm doing that exactly right now. Okay, so let's move forward. So this delta L of delta y, so this will be, this partial derivative will be minus x plus 2 lambda 1 y. Then you have another term which is minus lambda 3. Now, if you see such problem, so what you can notice is that, let me do this way. So let me write down another expression. So these are your two conditions. So this has to be 0. This has to be 0. So what you can do, you can write y equals to lambda 1 minus lambda 2. And from here, what you can write, your x equals to 2 lambda 1. I'll replace this y here and minus lambda 3. So you have expressed this x and y in terms of lambda 1, lambda 2, and lambda 3. Next, we have another condition which we call it as the complementary slackness that I have written before here, lambda times gx equals to 0. So you have three of them here. So it's lambda 1 times gx1, g1 of x, you can say that. So this is 1 is 0. Then you have this lambda 2 times of minus x is 0. So this is your complementary slackness conditions. And you have the third one, lambda 3 times of minus y equals to 0. So what you can do is that you can notice that you are trying to maximize this function xy. So if you are getting the value of x or y to be 0, and then you are not improving anything. So it's like the minimum that you can get because x and y both are greater than equals to 0. So what you can say is that x and y will never be 0 in this kind of setup. So that's why what you can directly write from here is that lambda 2 is 0 and lambda 3 is 0, since x and y cannot be 0. Since we are trying to maximize this product x times y. So now what you can do, you can put 0 here. So this will be 0. Then your lambda 3. So this part will be 0. This part lambda 2 also will be 0. So what you're left with is y is equal to lambda 1 and x is equals to 2 times lambda 1 square. So I hope this is correct. So let's move forward. So now you have your this equation. Here you can do, you can put the values of x and y. So this will be 2 lambda 1 square, and then y will be, this will be lambda 1 square, and this is minus 4. Now you have two conditions. One of them is lambda 1 equals to 0, but that will make your y and x to be 0. So that we don't want. So that means since this lambda 1 is not equals to 0, we are left with 3 lambda 1 square equals to 4. So this, the rest of the term should be 0. And you are getting lambda 1 square equals to 4 by 3. And lambda 1 is 2 by root 3. And if you put the values here, so you will get x is 2 times lambda 1 square. So it's 2 times 4 by 3. So this is 8 by 3. And your y is lambda 1, I guess. Yeah, so that's fine. So this is 2 by root 3. So this is your optimal solution. You can write it as x star and y star. So optimal solution. So this will make the product as the highest and also satisfying this constraint. So if you put x plus y square, so it will be 4. So that constraint will be active. So since the constraint is active, you don't care about the sign of lambda 1. So it may or may not be 0. So in this example, it turned out to be lambda1 to be positive. So that's how you typically solve this problems using this Lagrangian multiplier method. I hope this is clear. If not, you can ask me questions. And I'll take another example to solve such problems. So let's take another example. So I hope that will be more clear once I solve this second example. Okay, so this is example 2. So let me try and maximize z equals to 3x squared plus 2x plus 4y squared. So I think you'll find again the similar problem in your assignment as well. So I hope you'll be able to solve those once I go through this. And in your assignment, probably it will be pretty easy. Just by looking at the options, you can omit some choices and get to the answer. But you need to know the conventional way of doing or solving such problems. So that's what I'm going to show you. So let's try and solve this problem. So what's the first step in this kind of a setup? Uh, you will make a mistake if you don't convert this max to a min problem, because in your Lagrangian expression, it is all in terms of the function being in the min form. So let's try to do that. So this max of z, you can write it as min of minus z. So what you can do is you can write it as min of minus 3x squared minus 2x minus 4y squared. And let's try and write the Lagrangian function in this setup. So this Lagrangian function is again a function of x, y, and uh, you will have four probably, yeah, four lambdas here. So this will be lambda 1. Corresponding to this, you will have lambda 2, and corresponding to this, you will have lambda 3 and lambda 4. And also you need to convert this into this less than equals to type constraint. So this will be less than equals to 0. This will be x minus 2y minus 7 less than equals to 0. And this will be minus x less than equals to 0 and minus y less than equals to 0. So finally, you have got everything. You have converted your problem into the standard form. So that's the first step. So this will be again a function of lambda. So lambda will contain lambda 1 to lambda 4. And you can write your Lagrangian as follows. So this is the function expression. And then you will have this lambda 1 times x plus 3y minus 15 plus lambda 2 times x minus 2y minus 7 plus lambda 3 times minus x, and finally plus lambda 4 times minus y. And as before, this lambdas has to be greater than or equals to 0 since we are dealing with inequality constraints here. So let's try and get to the partial derivatives of this function. So you can write this as minus 6x minus 2, then you will have plus lambda 1, then plus lambda 2, then minus lambda 3. So this has to be equals to 0. This is your one equation. The other one will be with respect to y. So this will be minus 8y. And then you will have another term which is plus 3 lambda 1, then minus 2 lambda 2, and then minus of lambda 4. So this has to be equals to 0. So I have written it correctly. So you need not set delta L by delta lambdas to be 0 here, because that won't be 0. Because you will be left with the left hand side of this constraints, and that's not equals to 0. That's less than equals to 0. So that's typically one difference from the equality constraints, how you deal with these problems. So again, as before, what you can do, you can convert this x and y in terms of this lambda variables. So let's try to do that. So from here, you can write x equals to lambda 1 plus lambda 2 minus lambda 3 minus 2 divided by 6. And from here you can write your y equals to 3 lambda 1 minus 2 lambda 2 minus lambda 4 divided by 8. So now, as before, you can eliminate some of these lambdas, but it's a bit tricky here. In the previous problem, you could see the problem and tell that your lambda 2 and lambda 3 would be 0 because you are trying to maximize that function which contains x and y. But in this kind of a problem, you have to go through all the possible conditions and check for which condition you are getting the maximum value of the original function. So let's try to do that. So there is another condition which is complementary slackness condition. So this condition tells you that. So let's write down the easier ones probably. So the lambda 3 times minus x is 0. Lambda 4 times minus y is 0. And then what you are left with is, let's write down lambda, okay, maybe what I can do, uh, from here, you can notice that, okay, let's try and go the conventional way. Lambda 1 times x plus 3y minus 15, x plus 3y minus 15 equals to 0, and lambda 2 times x minus 2y minus 7 minus 2y minus 7 equals to 0. So you have this four conditions here, and from this you kind of have to like solve for these equations to get x star and y star. And you, in addition to that, you have these conditions that lambda 1, lambda 2, lambda 3, lambda 4 are greater than equals to 0. So let's try and do that. So what you can notice from here is that first, if you set your x and y's as before, all of them, both of them to 0, you will get a function value as 0. So obviously, you can notice that that's not an optimal solution because you can set your x and y to be 1 and 1, and then all these constraints will be satisfied and you will get a higher objective value. So from this, you can tell that both lambda 3 and lambda 4 will not be equals to 0. One of them still can be, but let's see if that happens or not. So let's try and do that. Suppose both lambda 3 and lambda 4 are 0. So what you are left with is x equals to this lambda 1 plus lambda 2 minus 2 divided by 6, and y equals to 3 lambda 1 minus 2 lambda 2 divided by 8. Now you can put this x and y's back in here in terms of this lambda 1 and lambda 2. And you can assume that lambda 1 and lambda 2 are not equals to 0, and you will get two equations and probably two unknowns of lambda 1 and lambda 2. And you can solve this and you can get to the final answer. So, and you can check for further things here from here. Suppose in this condition, if your lambda 1 is 0, then since your lambda 2 can be either 0 or it can be greater than equals to 0, and y cannot be negative, so that means lambda 1 equals to 0 has to imply lambda 2 will be 0. But in that case, what happens? Your lambda 1 and lambda 2, if it is 0, your x becomes negative. So that cannot happen. So that means you can say for certain that lambda 1 is not 0 in this setup. So lambda 1 is not equals to 0 when this two are true, lambda 3 and lambda 4. So this is wrong and this is right. So from here, Since lambda 1 is not equals to 0, you can get this expression x plus 3y minus 15 equals to 0. So this constraint will be an active constraint in this kind of setup. And now you can plug in those lambda 1 and lambda 2 values. And so if lambda 2 becomes 0, then what happens is that your lambda 1 can be 0 as well. So that's not a problem. So let's try and do that. So here, if you plug this in, this will be 3 times 3 lambda 1 minus 2 lambda 2 by 8. And that will be equals to 15. So now, if you just solve it, what you will get is that this will be 4 lambda 1 plus 4 lambda 2 minus 8. And you will, from this part, you will get 27 lambda 1 minus 18 lambda 2. So that's 6 times 3. Yeah, that's correct. So let me write it down clearly. So this is equals to 15. So what you're left with is 31 lambda 1 minus 14 lambda 2 is equals to 360 plus 8. So that's 368. So that's one equation. And from the other side, you will get another equation that will give you lambda 2 times x minus 2y minus 7. So that's x minus 2y. So that's 2y minus 7 equals to 0. Now, if you assume from this portion lambda 2 to be 0, then what will happen? You will get a lambda 1 value from here, and you can plug those back in here and here and get an x and y value. And you can get the function value from there, the original function value. So that's one possible solution. But if you don't set this lambda 2 equals to 0, then that's pretty simple because you are left with then another equation, which is this x minus 2y minus 7 equals to 0. So those both of this becomes an active constraint. So you can just solve these two equations in that case and get an x and y value and check for the function, check for z, and see which one is giving you the maximum value. So probably in this problem setup, you might find out that lambda 2 equals to 0 probably might be giving you a better solution. And from here, you can get the lambda 1 value. And probably you can plug in and get the correct answer. I may be wrong. Maybe this condition might also be giving you a higher objective function value. But that you have to check for. So here, as you can notice, is that we have satisfied all the conditions of optimality, like this gradient of the Lagrangian has to vanish and all those things, and primal and dual feasibility, complementary slackness. But ultimately, you have to check for which condition you are getting the maximum value. Probably this is happening because of local minima or something. That's probably the reason that I can find out. So this is all about this problem. So the rest of the problem, I think you can complete it just by looking at those conditions that I have talked about. And this is the typical way of solving such problems. And the key difference from the equality constraint part is that this lambdas has to be non-negative. Okay, so probably we can have another type of problem. Suppose I'm not solving that, but I'm just explaining what you have to do for that kind of setup. So typically these are for convex optimization problems. So typically your function is a convex function. So then only you can get to this global minima. So suppose you are given two both this condition, this gx less than equals to 0 and hx equals to 0. So these are your equality constraints. So suppose we have just one inequality constraint and one equality constraint. And you can write your Lagrangian as before. This will be a function of x lambda. So corresponding to this, you can imagine a Lagrangian multiplier lambda, and corresponding to this, you can imagine another multiplier called mu. So here you can write it in terms of fx plus lambda times gx plus mu times hx. So here also you will get this delta L of delta x equals to 0. So that's one condition. Obviously, both of these constraints has to satisfy. That's your primal feasibility. Then your dual feasibility will give you, corresponding to inequality constraint, you have this lambda greater than equals to 0. So this has to happen. But for mu, this is unrestricted. So it's not saying you anything whether it is 0 or greater than. So it can be greater than or less than or equality. Uh, so tied to 0. And you can notice that even if you write this hx as minus of hx equals to 0 and replace it by here, you will get the opposite sign of whatever you had of mu. So that's why this is unrestricted. And finally, corresponding to the complementary slackness condition, that sir kind of converted in the class by adding some plus yj square or something and made it as equality constraint. And with that, he got reached to that condition, this lambda times gx has to be greater than, equals to 0. So this is your complementary slackness condition. So if you solve this problems, typically will finally get to the final solution. So, and here also you typically don't know which are your active constraints. So you just plug in the values and solve it. And if this is a convex optimization problem, you're lucky to get to the global limit. Otherwise, you have to check for conditions for which one you are getting a higher value of objective function in case it's a maximization problem, and lower value of objective function in case of a minimization problem. Okay, so with that, I'll stop the discussion on this method, Lagrangian multiplier method. So there is another method. So let's start with that one. So that is the penalty function method. So this is the penalty function method. All right. So here also, what you can do that. So there are a few things I'd like to discuss. First is, okay, we have one more. Okay, so with the penalty function method, uh, one thing you have learned is the bracket operator. So that's, so let's try and see some concepts rather than solving some problems. I think in one of the assignment problems it is given as solved by penalty function method, but that doesn't quite make sense because you can solve it using any method and just see the options and get it done. But let's look at it more carefully in the concept point of view. So suppose I'm given some function min of fx, and then this is subjected to some constraint, say gx is greater than equals to 0, probably. So now what you are doing is that in case of penalty function method, and to be precise, probably with exterior penalty method, you might start with a solution which is not feasible. So what you can do, you can write another function, capital Fx, which is this first function, small fx, times one penalty term that you add. So this is your r, which is your penalty term. And then what you have this bracket operator of gx. So this can be as, you can put it as square as well, but typically you need not put it as square. So that's not a problem. You can keep it this way. And then for a greater than type problem, what your gx is that, so what is my aim here? I'm trying to minimize this function. So I'm adding some extra penalty term. And if I can minimize this term and can bring it down to as much as I can get to the optimal solution without violating the constraint. And if I violate the constraint, I kind of getting more and more penalty for that. So I am increasing my objective function value. So what I have to do that is here, if your constraint here is satisfied, you don't add anything here. But if it is not satisfied, then you have to add something here. So typically what you can do is you can write it down in this way. So this fx, you can write it down r times gx. So this is if your gx is less than 0. And since you have a restriction of the sign convention of this r, so r is positive, suppose. So that's why since this becomes negative, so we have to put a square here. So earlier probably I have told that you need not, but in case of this greater than type problem, you have to put a square here. So in case of a less than type problem, I don't think you need to put a square because the violation will only be positive. Okay, so in case you are satisfying that constraint, what you are doing, you are making it as 0. So if gx is greater than equals to 0. So essentially what I am doing is here, you can think this as min of 0 and gx. So if your gx is greater than equals to 0, you are getting back the minimization which is 0. But if your gx is less than 0, then that is less than the first term. So that means you are left with gx only, and you put that as penalty. So that's the main idea about this penalty function method. And there are different expressions of penalty terms that you can put. So I think in case of interior penalty method, what you can do, you can put this penalty function as 1 by gx as well. I think in one of the examples that was shown to you as well. So I think here it's kind of r by 1 by gx. And then since this term, if you're moving closer to that constraint line, so if you're in the feasible region, suppose this becomes a very large positive value, then this r can be a very large positive value to begin with, and you kind of bring it down and solve the problem. So that's the interior penalty method. So let's see the distinction between these two. So probably will be asked questions related to that as well. So this exterior penalty method, what this does, uh, you have to start with a very very low value of r, the penalty term, because otherwise your uh, gradient and those Hessians can be ill-defined and so on. So, and also if you notice that once you add this constraints in your objective function, you try to minimize this function capital Fx, and that becomes an unconstrained optimization problem. And you have already learned to solve those problems for a unimodal function. I think you have learned those techniques of region eliminations and so on. And also there are other techniques, say Newton-Raphson's method and all those things. With initial guess, you can get to the optimal point. If this is a convex function, you will hit the global optima. Otherwise, you might get to a local optima. So those things are still there in this kind of setup. And so let's get into the exterior penalty method. So here, what you do, you start with a value, start with a solution which is not feasible. So you're not in the feasible region, which is not feasible. And you are trying to get to the feasible region. So if this is your graph, and probably you have one constraint, say x equals to 3 greater, x, this is x equals to 3 line, and probably your constraint is on this side, so x greater than equals to 3. So probably your curve is looking like this. Probably the minima is somewhere here. I've not drawn it properly. You can start from here, but then you trying to get to the feasible region. So you'll move in this right direction. So in that case, you can add this penalty term. So this, suppose this fx plus r times of say gx, and this violation is if you are in the other region. So since you are in the greater less than equals to region, so this has to be a square term as well. And this r, you have to start with a small value and try to solve the problem. Otherwise, you might get to some point, you might skip some point, so that might happen. So you're gradually increasing this value of r and you're moving in this direction. So that's your exterior penalty method. Your interior penalty method is exactly opposite. So your interior penalty method, you're penalizing everything for the feasible region. So penalize for being in the feasible region, but if you're away from the optimal point, then your penalization is more, otherwise it's less. So this is penalized in the feasible region. And this is also, this function, suppose it's like this, you start with probably some this point, then you probably have to go here or something. So it's this R value, initial R is high, and then you solve the optimization problems, unconstrained optimization problems, you get an improved value of x and y. You again decrease your value of R, so R is kind of decreasing across iterations here. So that's the main idea of this penalty function methods. So let me see what else I had in mind to discuss. Okay, so I think I had, so sir, I think given one example of penalty function method. So this is example one of this method. So I think if you are given one function like x1 minus 2 square plus x2 minus 3 square, so this is a convex function, so not a problem, and subjected to say x1 plus x2 minus 4 equals to 0. So hello, do you have any question, Pankaj? Yeah, so this is a 2D problem. Yeah. Hello. Yeah. Is that clear? Oh, how can you draw in three dimension? Okay, so it's hard to draw on a paper, so I cannot draw it in my tab. So you can probably plot it in some kind of solver, maybe some Excel plot probably you can do, or you can do some programming language kind of plot, or probably you can find something online as well, and you can plot these functions. But it's very hard to like show it on a piece of paper because you don't have the third dimension here, right? Yeah, so it's so drawing wise, you need not worry about that in such problems. You can always like search it up online tools and everything and get the plot of that. So not a problem. Okay, so yeah. So let's try and solve this. So since this is an equality type problem, so what we have to do, you kind of have to add one parabolic kind of penalty term. So I think that was also discussed in the class. So your fx now becomes this first fx, then r. So so suppose there are two violations here. Earlier there was, if that the constraint was greater than equals to type, the violation was when that was less than, or the function was less than equals to type, the violation was greater than. Here, if it is an equality type constraint, the violation is either greater than or less than. So either this value becomes positive or this value becomes negative, and we have to penalize for both those sides. So that's why what we do, we take this function and we just square it. So that means the negative terms also will add up here, and the positive terms are already was adding up, and you can write this as compactly. So that's the idea of how why you have to use a parabolic function here. And the way of solving now is that you have to like start with a point which is not on this line, because you know that this function you don't know the exact point. Suppose you can start with probably 1 and 3, so that will be your interior penalty method. But again, it might not be the optimal way of doing it, but it might also hit the optimal point as well. So that's not an issue. So suppose I'm using exterior penalty method. So that means I'm starting with something which is having violation of this constraint. So the advantage of exterior penalty method is that you can always start with an R value which is small. But interior penalty method, you have to start with an R value which is large, and you don't know upfront how large that value must be set. So let's use the exterior penalty method. So you can start with say x1 equals to say 2, and x3 equals to, sorry, x2 equals to, x1 equals to 2 and x2 equals to 3. So there is a violation here because this left hand side becomes 1 in that case. And this is an exterior penalty method. So you have to start with an R value which is very low. So suppose you can start with, and that's not equals to 0 obviously because you are penalizing. So you can start with say zero point 0.5 or zero point 0.2 or something, so zero point 0.5. Then what will happen? Your converted function now will look like x1 minus 2 square, x2 minus 3 square. And also you need not put these values here because ultimately right now, because ultimately you're solving this. So what you can do, this function is now a 2D function and unconstrained function. You can minimize it and get to your next x1 and x2. You can get to your next x1 and x2, and then again check whether you violate this constraint or not. If there is violation, that means again this is an exterior penalty method, so you have to increase the value of r, and again you have to replace it here, and using that as an initial point or something, you can get to the next solution point. So that's the idea of solving such problems using the penalty function method. But I think in your assignment problem, there is one problem. I think it was given, suppose I'm writing it down. So this is example 2, say. So I think it was given something like this. This like cube, this is 2. Yeah, I think you are given some simple problem like this. Uh, so let me do one thing. Let me put, so 1/3 can be anything. So let me put this 1/10. Let me put this x plus 4. I'm just changing the values a bit. So now, and also probably you can put this as 2. So just, so here what you can get is that x1 is greater than equals to 2. And from here you can get is that x2 is greater than equals to 0. So, and since this is a minimization problem, you just set everything to its lower bound because this is the lower bound, because anything greater than this will only increase this part and this part. So you set x2 equals to 0, x1 equals to 2, and you minimize this function. It's as simple as that. So I think something similar is asked in the assignment. You don't even need penalty function method for that. I don't know why the question, whoever has set it set like that, but yeah, the type of questions you might get from penalty function method is that you are given some R value to begin with, and you are given some x1 and x2 values. And then what you do, you just evaluate the function, and then what is the violation, and you keep doing that. So that's probably we asked like, what is the violation after first iteration, or how much you are off from the this constraint after the first iteration. So you can create one table like this. So probably this is your iteration. And you can solve these problems in Excel as well. When you are given a large problem, this is x1, x2, fx, this is hx, so this is the equality constraint value, and then this is your f value. So ultimately, after few iterations, this hx has to go to 0, and this fx and capital Fx has to match, because if your fx gets to 0, your violation and penalty, everything will go to 0. So it's like in iteration 1, you can start with, uh, say, in the problem that I have shown you, it's 2 and 3. You put 2, 3, you put those in the small fx function, you probably will get 0, right? And here you will get hx equals to 1, and your this value will be zero point 0.5 times 1. So this will be zero point 0.5. Now, so here you can also write r. So r is zero point 0.5. In iteration 2, what you can do, you increase this r value. So suppose 1 or maybe 10 or something, and then again get this. And just like this jump should not be too high, because you might miss the optima in that case. But yeah, you increase slowly the stars one by one, and you probably get the final value. Okay. So yeah, I think I wanted to discuss this topics only. Okay. So any doubts that you have, or any questions related to assignment, or anything from the previous week, or anything, like any doubts or anything? Okay, probably not. Or you can ask in the next 5 minutes. So I think also one of the questions, have you to like checked the assignment of this week, like assignment 6? Uh, were you able to like notice if there were issues with some questions or not, or something like that? Okay, so I think there was one problem where there was an issue of some problem with electrical circuit that was given, and I think one of the question was fine, the first one, but second one I think has some issues. It was not clear about what was being asked. So probably we'll talk to the other TA, and that might be like removed from the evaluation or something. So let's see how that goes. So I think this week's content was pretty simpler than the previous one. So just be careful with the inequality constraints and the signs of those lambdas that I talked about. Corresponding to those lambdas, you have to take it as greater than equals to 0. In terms of like equality constraint, doesn't have any restrictions on the signs of the Lagrangian multiplier. So that's the things that you have to keep in mind. And one last thing is that in this penalty function method, this extra term that we add is uh, kind of analogous to the extra term that we add in the Lagrangian function. So if you are asked to like relate this to the Lagrangian function, you can always put the Lagrangian function in terms of this penalty terms as well. So you might get one question related to that. So it's pretty simple. You just write the Lagrangian function and equate it to this penalty term function, and see what kind of violation that you make. So in terms of that, you have to write it in terms of max or min type problem, and then finally get to the answer. So that is all about this week's content. So Pankaj, if you have any questions, you can ask. Otherwise, I'll close the session, and other TA probably will be taking the other session. Yeah, yeah, sure. Thanks.